Hi, and welcome to a quick refresher on balancing chemical equations. We're just going to go through some simple steps on how to balance. If you're confident with this, maybe just write down some key points on remembering the different types of equations and then move on to practicing and doing your quiz. Let's get started. So before we can balance an equation, we need to remember that there is a law in the universe that we refer to as the law of conservation of matter. Essentially what this says is that during a chemical reaction, or really in anything in our universe, matter cannot be destroyed or created. So all the matter in our universe was here at the beginning of our universe and continues to be here. So it's sort of like a closed system. What this means is that if I start off with a number of atoms in my reactants, then I must have that same number of atoms in my products. And if the flasks that I'm doing my reaction in stays closed, then the mass won't change either. So the mass of my reactants must equal the mass of my products, which is a really great thing for us to be able to do when we're trying to work out how much of something has reacted. So one of the other things that we need to be able to do is to remember essentially the anatomy of our chemical reaction, that we have reactants on the left-hand side and then we have products on the right-hand side, and that the thing in the middle should be an arrow, and this arrow indicates that a change is occurring. So we don't use an equal sign because what's on the left does not equal what's on the right. They've been rearranged and changed into something new, even though the atoms are all the same. So it's putting together Lego bricks in a different way and creating something new. In order to be able to fully understand this, we need to be able to define each of the other components of a chemical reaction. So this includes our states, coefficients, and subscripts. Our states, if you remember, are the different things that let us know what physical state the reactants and products are in. So we have, we use a little S for solid, then we have an L for liquid, AQ for an aqueous solution, anything dissolved up in water, and then we also have gas, our highest energy of state of matter, so where particles are moving around really quickly. So these are our states, and our coefficients are the large numbers in front of our species that are reacting. So species we often use to define just the individual compounds that are reacting. So if I took, let's say, hydrogen gas and oxygen gas and reacted it to make water, then hydrogen is one species in this equation, oxygen is another, and then water is the final product species that we're forming. In this equation, we can see that two hydrogens react with one oxygen, and we will produce two lots of water in this process. So this large number at the front here, this is our coefficient, and they are the numbers that we change in order to balance a chemical equation. Our subscripts are the smaller numbers that we make small and just below the line of our text, and they are there to set the formula of the compound. We can't change those when we're balancing because then we change the nature of what's reacting, and that's not what we're doing. Hydrogen gas reacts with oxygen gas to produce water. I can't make that single hydrogen or change the formula of water to H2O2 because then I'm not talking about the same things. When I change the subscript, I change what it is that I'm physically talking about. And then the reaction or the equation would technically be incorrect because those compounds may not react in the same way. Our steps for balancing our chemical equations, we need to determine what our reactants are and what our products are. So this may be, in the case of our reactants, we may see terms being used like sodium is placed into water and a reaction occurs, in which case sodium and water would be our reactants. It could be, let's say, as in our previous example, hydrogen and oxygen were placed into a flask and added a catalyst which caused them to react, and water was formed. In that case, we would know that hydrogen and oxygen are our reactants, and water, because it said it was formed, is our product. So we're going to have a lot of practice in pulling out equations from written descriptions, as well as being able to balance them, because it's really a key skill that we need in chemistry. Once we've identified our left-hand side and our right-hand side and separated them by an arrow, then we need to work out the number of atoms for each element. Okay, so we, in the case of water, would have our H2O, so we have 2 hydrogens and 1 oxygen. Once we've worked this out, we can pick an element that is not equal on both sides of the equation. I usually start with something that turns up only once, and as a rule, always leave oxygen till last, because oxygens are usually a bit tricky, usually turns up in more than one species, so we need to balance everything else before we can balance the oxygen. Once we do that, we can add the coefficients in front of the formula to help them balance out, remembering that when we add a coefficient, we are multiplying by that number. It's like putting a number outside a bracket in algebra. Okay, so the coefficients multiply out the number of elements in that compound. So if I put a 2 in front of our water here, then I have 2 lots of 2 hydrogens, so that gives me 4, and I have 2 oxygens. So remembering that it acts just like a number outside a bracket in algebra. And then once we do that, we can keep working backwards and forwards from left to right, until we have an equal number of atoms on each side, and we can say that our equation is balanced. Let's have a bit of practice. Okay, so we've got P4O10, so tetraphosphorus decaoxygen for this one, or we just tend to refer to it as P4O10. So now let's have a look. I've got phosphorus and oxygen, hydrogen and oxygen, and then in my products I've got phosphoric acid. So I've got hydrogen and PO4. What I can see here is I've got 4 P's, so I'm going to make this 4 over here as the first thing I do, and now I can see that my phosphorus, I've got 4 over here and I have 4 over here, so they're both balanced. Then I'm going to skip over my oxygen, because as I said, they are often usually the trickiest ones and we leave those to last. Now I can see I have 2 hydrogens here, but I have 4 times 3 hydrogens on my right-hand side, which is actually 12 hydrogens. I get to 12 by multiplying 2 by 6. So if I make it 6 here, I get 12 hydrogens. Now I can double check my oxygens and see what's going on there. I have 4 times 4 oxygens over here, which is 16. I have 6 oxygens here, and then I have 10 oxygens here. So I actually have got all of them balanced. So if we get rid of all our little marks for thinking here, I can now see that I am balanced. The last thing I need to be able to do is to put in my states, and P4O10, like most oxides, will be a solid, water is a liquid, and then H3PO4 is going to be aqueous because it's an acid. Okay, so that's the first one done. Have a pause, try and balance the other ones, and then come back and see what the answers are. Okay, looking at this one, we have a neutralization reaction because we have an acid plus a base going to water plus a salt. So I'm going to start off with the thing that doesn't change on each side, which is the sulfate. So I know that that's actually balanced, so I can ignore that now in the rest of my equation until I've figured out if I need to multiply by 2. So now the next thing I'm going to do is I'm actually going to do my sodium, because it turns up in one place on the left-hand side and one place on the right-hand side, whereas my hydrogens and oxygens are all over the place. So if I have a look here, I have 1 sodium here and 2 on the right-hand side, so I'm going to make this a 2. Now if I look back on my right-hand side, I have 2 hydrogens and 1 oxygen, but I can see straight away, what have I got here? I've got 1, 2, 3, 4 hydrogens and 2 oxygens, which means if I do this, if I make 2 waters, this gives me 2 oxygens and 4 hydrogens, and I'm balanced. Last one is a combustion reaction. Oops, we just forgot our states, so we'll put in aqueous because it's a acid, aqueous because it'll be a solution of a base, liquid, and then this will be aqueous as well. Okay, so the last one is a combustion reaction. I have a fuel reacting with oxygen to give me CO2 and H2O. So anytime I see a compound like this C2H6 reacting with oxygen, it should trigger that it's a combustion reaction. We're burning the fuel in the presence of oxygen, which means we will, if it's complete combustion, end up with carbon dioxide and water. So we follow our rules again. I'm going to start with carbon because it turns up in one place. So that means that I will change this to 2. I'm then going to do my hydrogens because I leave oxygen to last because it's in more than one place. So hydrogen 6 on the left-hand side and 2 on the right-hand side. So 3 times 2 will give me 6. Okay, so now I check my oxygens and work out what's going on. And I have 3 and 4, so I have 7 oxygens. Quite often, if I have 7 oxygens, when I've got an odd number on the right-hand side and oxygen only coming as oxygen gas on the left-hand side, that means that I would have 7 divided by 2, which is not a whole number, which means I need to multiply my entire equation by 2 in order to make everything a whole number. So if I do that, let's get rid of our divided by 2's and our coefficients. So if I multiply everything by 2, I'm going to get 2 here, 7. This was 2, so this is going to be 4. And then this was 3, so this would be 6. Put in my states. This will be a gas. This is ethane. Anything less than 4 carbons will be a gas. Oxygen is going to be a gas. Carbon dioxide is going to be a gas. And water will be a liquid. Okay, so that's our examples. Hopefully you remember what you're doing and you've got a lot of practice to do.